All right, section 11.2, we're going to take a look at vectors in space. And before we actually get to the vectors in space, we're going to take a look just at points, lines, curves, those kinds of things, just in general, how space works, okay? So for starters, we're going to extend our ideas from R2, right, the real number system in 2 dimensions, to R3. We specify a point by x, y, z. And the first thing we're going to do is plot points, okay? So plotting points takes a little bit of imagination, okay? And if you're not good at it, it's okay. I'm not going to claim to be fabulous at it either. But we're going to draw things three-dimensionally. To start out with, our three-dimensional graph is going to look something like this. Okay. Standard, of course, of operation is that x is on the left, the y is on the right, and the z is the vertical one up. So if you do it differently, it's not going to hurt anything. This is just what standard you see. I don't know why.
They change it from y going up.
I don't know. I don't know. But this is how you see it typically done. So we'll go with what they do. But if you did change it, it wouldn't hurt my feelings. But you might get it graded wrong because I might not be thinking clearly about what you're doing when you do it. So if you just do it with the way that they do it, it would probably make it easier for all of us. All right, so we've got 3, 1, and -5. So 3 is just fine. We're just going to come out 3, right? And I need to go over 1 on y, but I need to go over 1 on y parallel to the y-axis. So what ends up happening, if I were just plotting this point, I'll plot it in white, I'll plot my final answer in yellow, is that I would be somewhere about right here. Oh, I said yellow. I changed it to red. Does that make sense? Can you think about that sort of in terms of I'm going to do this actually. Let's go with orange. So you can kind of picture here, we've got this kind of a imaginary orientation going on. From the white point that I have, I'm supposed to go -5, which would mean 5 down, right? The vertical axis is going straight up and down, so I need to go 5 down from here. So I'm going straight down like this. And I want my dimension or my measurements to be sort of equal in value. So I'm going to count and try to make my spacing the same. So this point right here is where I would end. Now, there's nothing wrong with leaving it like that, but there is a way to make this feel a little bit more three-dimensional. The way to make this feel more three-dimensional is actually to draw in that same like downward, dotted, orange line that I have, by doing that along the other axes as well. So take a look at this. If I were to come down and try to draw, that's not great, this piece that looks like it's parallel to the piece I did above, and if I were to do the same thing over here, I could have done better. Let's try a little bit better. That's not bad. You see the box now? Can you kind of squint and see what yours? Mine looks like a box. I have the unfair advantage of technology, right? So you squint a little bit and see the three-dimensional box. That's what's going on, right? This is a three-dimensional quantity, okay? So do you have to draw the dotted lines? No, you certainly don't. You're looking for the general kind of movements that we've made. You're not going to graph a whole bunch of these suckers, but this is what we would be looking for. Okay? Okay, so what we're going to do next is we're going to do a bunch of different problems that are sort of variations of things you've done in 2 dimensions and see how it affects things in 3 dimensions. So everything we're doing is stuff from like Algebra 1 and Algebra 2 in the next few problems, okay? And it's just extending it to a 3rd dimension. So this next one is distance formula. You know what the distance formula looks like in 2 dimensions, right? You take the square root and you take, yeah, we're fine. You take the square root and then you do the difference in the x values, you do the difference in the y values. Well, so now we're going to do the difference in the x values, the difference in the y values, and the difference in the z values. So I've got, if you want to be really clear about the ordering, which I guess I will on this one, we're going to do this as our second ordered pair of points over here. And so we're going to start with them. So I'm going to do 5 minus the x value 2, plus I'd have 5 minus my y value in the first point, 1 squared, and then I would have the 2 minus the 2 squared. Because we're squaring everything, this one's kind of nice because none of them ended up being negative. What you're going to see me doing pretty quickly is ignoring which direction I go because I'm going to square them anyway, right? I really just want to know how far apart they are. So on this one, it didn't end up mattering, but in the future, we're going to see some values where I'm going to change that up a little bit. So this is 3 squared plus 4 squared, and then I've got 0 squared. So 3 squared is 9, so 9 and 16, which is 25, and you've got 5. So do we need to see every single one of those steps? No, I don't need to see all those steps, but you should show me a couple steps along the way of what's going on with the inside. That way, if you make a mistake, we got some partial credit we can offer and stuff like that, and I don't have to guess at what you're doing, okay? So distance, it works the same way, just you've got a third little component at the end. Okay, now imagine you've got a triangle in 3 dimensions. It's not a triangle in the XY plane, it's a triangle in the XYZ system, right? So imagine, like we've got this classroom, we're in 3 dimensions. So imagine having something where the corner up here is one of our points, and maybe the corner back here by Noah on the floor is one of the points, and maybe where this wall piece hits over here, right, the brown part is another one of the points. So none of them are in the same XYZ planes at all. Like you can't put it into a single plane, right? We're in a true 3 dimension. So this is asking us to find the lengths of the sides and then to decide if it's right, isosceles, or neither. So the things that determine about right and isosceles, you may or may not remember, but you will as soon as I say it, right? Isosceles means what's true about the triangle.
2 sides have the same length.
2 sides have the same length. So we're going to have to find the side lengths to do that, but it asks me to do that anyway, right? So once I find the side lengths, I'll be able to make that a claim. If it didn't have 2 sides that are the same length, and actually, even if it did, it could be a right triangle. Have you seen a right isosceles triangle before? Sure, absolutely, right? A right isosceles triangle would just mean that the 2 legs here are the same length, like that, right? 1, 1 square root of 2. So it could be that as well. But what has to be true about about a right triangle in order for it to be right?
Has to make a 90-degree angle.
Okay, it has to make a 90-degree angle. What else? The Pythagorean theorem would have to hold, right? So we would be checking to see if the Pythagorean theorem holds. So we're looking for the sides to match or not match, and then we're looking at whether the Pythagorean theorem holds. And it could be right and nothing else. It could be isosceles and nothing else, or it could be right and isosceles. All those options are available to us, correct? Okay, so we're going to find the side lengths. And I left them off, even though in terms of my notes it would have been nice to have them on, because your book tends to leave them off too. We need to have a way to identify these points, so I'm going to label them A, B, and C for the purposes of us talking about them together. It'll make it easier. And you can do the same thing in your notes, or in your homework, if you will, as well, if you wish as well. So we're going to do AB. Notice that I don't put anything on top of AB. And again, from a geometric standpoint and what you've had recently and so forth, I don't know if you remember, when you actually put the segment on top of it, it's talking about the segment. When you leave it off, it's talking about the length of it. So we don't actually put the notation on top of there right now because we really do want the length. So finding length is the same thing as the last problem we did. It's the same as the distance formula, right? So we're actually going to take these one at a time with points A and B. So as you take a look at this, x value of point A is the same, so that's 0 squared. I'll put them in as placeholders just to keep our minds clear about what's happening. The y values are how far apart? 5. 1, 0, 1's 5, so that's 5 squared. And how about the z values? 4. Okay, so I don't need signs at all because I'm going to square the things anyway, right? So I can sort of jump ahead and not worry about quite the amount of detail that, of course, you would work with if you were teaching the Algebra 2 kids, right? If you were doing this in Algebra 2 or college algebra here on campus, I wouldn't do this, but you certainly can because we can see that. All right, so I have 5 squared, so that's 25. 4 squared is 16. What is 25 plus 16?
39.
41.
Oh.
Yep,
Oh.
it's okay.
My calculator.
Okay. All right, square root of 41. Now, that doesn't help us right now, but it's one of the 3 things we're going to look for. So that's AB. Let's do AC next. So A and C, they're the furthest apart on here. So the x values between A and C, how far apart are those?
2.
2. So 2 squared. Y values?
1.
1. So 1 squared. And the z values?
3.
3. Okay, is everybody clear where those numbers are coming from? Now is the time to ask if you're not. Okay, we're good? Excellent. So this gives me 4 plus 1 plus 9, which is a total of 14. Square root 14. Okay, so far, this is not looking promising for isosceles. At least those two didn't match, right? I mean, it's not isosceles yet from our perspective. The last one I need is BC. So between B and C, the difference between the x values,
4. Oh, no, sorry.
2, 2 squared. The y values,
6.
6. That's the biggest one we've had so far. And then the z values, 1. Okay, so I have 4 plus 36 plus 1, which is 41. Okay, what do we know? Definitely isosceles. Okay, so we have isosceles. So we can't just automatically be done. We need to actually still consider, is it a right triangle? Noah says no. How come, Noah?
Because a right triangle, the hypotenuse is longer than the other two, and there's 2 radical 41s, and
Yeah.
the last leg is shorter.
Exactly. Everybody good with that? Yeah. The third side that's not equal is not the longest side here, so we don't have to even test that. Now let's just say for a moment that it didn't say square root 14 on that one. It said square root, like 79 or something like that. Then we'd actually have to put it into, the equation of the Pythagorean theorem and see if it's equal on both sides. We'd have to check it. But here we can easily dismiss that possibility and not have to do so. So we have an isosceles triangle here.
Are you cool if we just put isosceles, or do you want us to also specify, not a right triangle?
As long as you just put the isosceles, I'm going to know by the fact that you didn't show any. Well, that's a good point because we didn't actually show it. So inside of WebAssign, it's not going to say anything probably, right? Or it's going to do it a multiple choice kind of thing. So that's probably going to be obvious there. So let's in fact, say that it's not right. I think that's a very good point.
Tuesday's right triangle due to shorter.
Sure, that would be fine. Yeah.
I'm just hypothesis.
Yeah, the shorter third side or the unequal third side. Yeah. Okay, midpoint. How do you find midpoint?
First plus second over 2.
First plus second over 2, right? So we do like our x coordinates over 2. So 3 plus 1 over 2. Our y coordinates over 2. That's what we've known so far. And by natural extension, z is going to do the same thing, right? 6 plus 0 over 2. All right, so 3 plus 1 over 2. What does that give me? 2. How about the y value?
6.
And the z value? Okay, so are you liking section 11.2 so far?
Yes.
Just chapter 11 in and of itself is fantastic. Okay, equations of a sphere. Now, we haven't actually done equations of a sphere in class yet, but you've done something that's equivalent in 2 dimensions. You've done circles. So how does it work differently? Well, you just have a third component, just like you did with the midpoint a minute ago, right? So our center is 3, 1, 4. So we'd have x minus 3 squared. And they are squared, by the way. It is still squared. It's not cubing anything. X minus 3 squared. How about the y?
Y minus 1 squared.
Y minus 1 squared. Z?
Z minus 4 squared.
Mm-hmm. And what do you think it should equal?
R squared?
4.
R squared, which is 4. Just exactly like that.
Isn't ellipse the same way? Like, would you just
Mhm.
do over
Yeah.
whatever
Mhm.
the...
Yep, it would be. Okay, ready for 3? Or not 3, 7, 6 rather. I don't know why I said 3, 6. Okay, so now we're going to actually take something that's given to us in this sort of ugly form, and we're going to turn it into a sphere form. And I purposely left off part of the directions that told you what to do because I think you should know what to do without them being told. What do you need to do here? Yes, it's completing the square, right? You should know to complete the square here. This is just an extension. So the pieces that have x, y, and z are all going to be separated a little bit, just like we would do when we had x's and y's. So x squared, minus 2x, and we'll leave a space. Y squared is its own. There's no other y's, so that part's fine. and then z squared minus 4z, and we'll leave a space, and it equals 0. Just spacing some things out. All right, so what goes after the negative 2x? Plus 1. Okay, and if you remember, the way Noah got that is you take that middle term, the negative 2, you divide it by 2, and you square it. But if I added a 1 to the left, I do, I add 1 to the right. Okay, we don't have to do anything for y. We get that one's kind of for free. How about the z component? What's going to go after the negative 4z? 4. Plus 4. So I divide by 2, I get the negative 2. But then when I square it, I get the positive 4. And that by turn also means I have a positive 4 on the right. So as you remember, these all factor beautifully. That's the point of completing the squares, that they're going to factor as perfect square trinomials, which is the reason in college algebra that we talk about perfect square trinomials, even though they aren't really necessary at that point, is because for factoring purposes, they factor so nicely. So this one would factor as x minus 1 squared, have y squared, and then z minus 2 squared. And on the right, I have 0, 1, and 4 added together would give you a 5. So that's part of what it asked me to do, put it in standard form. It also asks me, once it's in standard form, what's the center? So what would that be?
1, 0, 2.
1, 0, 2, yes. And do remember that the signs are flipped, right? Because it's the subtraction as a part of the formula. And then what is my radius? Square root of 5. So all of that is the answers it was looking for. Okay, so all of that was introduction to 3 dimensions. You may have seen some of that before. I kind of hope you have, but if you haven't, it's not difficult. As you saw, everything just takes on this third piece that looks just like the other 2 pieces. Now we're actually going to do the vector stuff, okay? So it's not any different though, right? The vector stuff works just like it did when we were doing the vectors before. We're just adding a third component, just like we did with all the things we've added components to here. So we're going to find a vector and its magnitude. And now it does matter that I do my subtraction in the right order, right? It's terminal point minus starting point because I'm not squaring things. So I do want to be careful that I get these in the right order. So here's my vector that we're going to look at. We'll call it v. So if I do my terminal point minus my starting point, I'd have 4 minus 3. You can either write it or just do it. And then I'd have 1 minus 2. And I'd have 6, minus 0. You can write it in IJK form if you wish. But we'd have 1, negative 1, 6. No different than what we did before. But now I'm also asked for the magnitude. So now I can kind of ignore the signs if I wish. This would be 1 squared, and 6 squared. So what would that give me when squared and added? Squared 38. Okay, so we're going to use this vector. I probably should shift it to the next slide too so that I have a copy of it. So this is my vector up here. And we're going to find the corresponding scalar multiples of vectors. We did this in section 11.1 as well. So the first one is 2v. So we're going to double everything. What would we get?
2, negative 2, 12.
Perfect. What about negative v?
Negative 1, 1, 6.
Spacing issues. There we go. Good. And what about 2/3 v? Everybody loves fractions, right?
2/3.
Yeah,
negative
2/3.
4.
Yeah. Is it 4?
Yeah.
Yeah, 4. I think I changed this then.
3.
Okay, cool. All right. Everybody good? Well, that looks good. Excellent. All right, so let's do some vector combinations now. So this was actually scalars for vectors, but now we're going to combine some vectors. So I have 3 different vectors I'm given, u, v, and w. Feel free to do this in component form or the IJK form. Either of those are fine. I've written mine out in components, so I'm going to do that way. So my z is actually defined to be u minus 2 times v plus 3v. If you want, you could actually find the negative 2v and the 3w. That might actually simplify it to be a little bit cleaner to work through if you want to do it that way. Or you can just do it all in one fell swoop. So I'm going to write mine out in all one fell swoop, but feel free to do it differently if you would like. So we need to have the vector u and its x component, which is 1, minus 2 times the x component of v, which is also 1, plus 3 times the, I'll say I component is what I should be saying, the I component of vector w, which is a 2. And that is my first component, my I component of my vector z. The next one, we're going to do the same corresponding pieces, but with the different values for j. So I have the j component first, which is negative 4, minus 2 times the k component, which is, the j component of v, which is negative 3. And then plus 3 times the j component of w, which is 1. And then my last one is the k component, so negative 2, minus 2 times the k component of v, which is 4. And then plus 3 times the k component of w, which is negative 1. Okay. I actually think after having said it, I liked what they suggested to do better, but that's okay. Did I make a mistake? I was trying to be really careful. Where did I make a mistake, Alex?
I think that you forgot to multiply it by the scalar on the second two for v and w on the last one, because it's, oh, never mind.
I think they're there.
Okay, I was just listening to you, then when I looked up. It's
I may have said it wrong, but I think I wrote it right.
You wrote it right, I think.
Okay.
I just heard it wrong.
Okay, and I wasn't even going off of what I wrote down before. I was trying to recreate it to see, and I've recreated it the same way I created it the first time, so I think I got everything in there. Okay, one way or another. Hopefully we've got all the pieces. I've got 1 minus 2 plus 6. 5. And then I have negative 4 plus 6 plus 3. I have 5 written down. Is it 5?
That's what I got.
Negative 4 plus 6 plus 3.
6, yeah.
Yeah, my 3 is kind of running into this negative next to it. Move that over. Okay, so I think I have 5 again. And then the last one is negative 2 minus 8 minus 3. Is it negative 11?
Negative 13.
I have negative 13. Okay. So for all of the simple little arithmetic stuff, we want to be really careful, which is why I was doing what I was doing, is to try to be really careful. Okay, very good. So this is our vector z with those conditions. How do I find the magnitude of z? It's the distance formula, right? I mean, yeah, it's the distance formula with those individual components. So the magnitude of z is the square root of 5 squared plus 5 squared plus 13 squared. What's that as a total?
Radical 219.
219. Somebody decided, I don't have any simplification for this, so I have a feeling it doesn't simplify. Somebody
I
just
do.
check that real
I
quick.
tried to divide it by 2, and I tried to divide
So
it by 3.
it divides by 3, which goes to 73, which then.
Oh, and 73 is prime as well. Okay, cool. So 3 and 73, which doesn't help us. Very good. Okay, cool. That's what my kids have been doing right now in Algebra 1 is factor trees. So, yeah. Okay, how about a unit vector? A unit vector, oh, let me get this vector here. We'll copy it for the next page. A unit vector for this, so here's my vector, and its magnitude was the square root of 219. So how would I find a unit vector in the direction of z?
Divided by the magnitude.
Yeah, I'll divide the 5, the negative 13, all by square root 219. But of course, it's going to give me a square root 219 in the denominator, which I will rationalize. So, in an effort to only write it down one time, I'll do both at the same time. So this is 5 square root 219 over 219. Is everybody okay with me jumping that step? Excellent. We'll do it again. 5 square root of 219 over 219. And then negative 13 square root 219 over 219. Okay? What do you think it means for it to be the opposite direction of Z? Yeah.
Just negative.
It's just negatives. So pay attention, whether it's in the direction or the opposite direction of, but the process is not hard. Just pay attention to it, right? So my signs are all going to switch. So I have negative 5 square root 219 over 219. Another negative 5 square root 219 over 219. And then positive on this one, 13 square root 219 over 219. Okay, how are we doing? Good so far? Excellent. The last two things are maybe the most visually different than we've seen already. It has to do with parallel vectors and collinear points. So parallel vectors, it's the very bottom of your page number 3. It's talking about how we decide if vectors are parallel. So one of the things I want to remind you going into this definition is that we said that two vectors are equivalent if they're, no matter where their initial and terminal points are, as long as they're in the same direction. Do you remember that? So we could draw them starting anywhere and ending anywhere as long as the x and the y, the slope basically of what we were doing and the length is the same. So as long as the direction and the magnitude are the same, we call them equivalent vectors. So they're not parallel, right? That's what they look like when we draw them. And I drew a picture of ones like that looked like this. Do you remember that picture last time? I'm not going to draw the scale in for it, but it looked like this. And we said they're really the same. But if we look at them from our normal perspective of lines, they would look like they're parallel. But these are not parallel. These are actually equivalent. So our definition of parallel is going to look a little bit different than you might expect. Two non-zero vectors u and v are parallel when there is a scalar such that the u is equal to c times the v. So the difference is, while these two are equivalent, if I extended the length of one of these two would be parallel. Okay, so their direction is still the same, but their magnitudes are different. That's the primary difference. Okay, direction is still the same, magnitudes are different. So when we're trying to decide if the following are actually parallel, what we're trying to decide is if they have the same vector, but maybe off by a scalar multiple. So we're going to consider the vector z, and we're going to do this first one that's letter A. And what we're asking ourselves is there some scalar multiple, either a fraction or a decimal or even a whole number, right, that we could multiply the first one by or divide the first one by because they're equivalent operations and get the second one? Is there?
Yes.
Yes, there is. What would c have to be for that to work?
Negative 2.
-2. So if c is equal to -2, this works, and that's why that this would be called a parallel vector to the first one. Sorry, let's try this again. I'll move these over so I have more space. Okay, so now we're back to, the beginning. C as well, back to z, the way we started with. And now we have 2 4/3, -10/3.
Yep.
It works.
2/3.
C is 2/3. So they do not have to be, whole numbers. They can also be fractions. So this one's parallel.
Is that 2/3 or 3/2?
It depends on which direction you go. If you're talking about going from Z into part B, it would be 2/3. But if you're thinking about going back the other direction, it'd be 3/2. Right? So if I were, you see what I'm saying?
Yeah.
So the scalar multiple could be written either direction, depending on where you're sort of considering your first one versus your second one. It doesn't make any difference.
So A could have been -1/2 also.
Yes, correct. We could have done -1/2 for A if we considered going back the other direction. And sometimes it's easier to see from one direction than the other.
Yeah.
So that totally is fine if you see it the other direction. I don't know what WebAssign might do. So if you're pretty sure you got it right, you might try and flip your fraction upside down. That's a possibility. But I would certainly accept it at either perspective on your work for me, your written work. How about C?
No.
No. It's an easy no if you're thinking about it correctly. If it's an easy no, why it's an easy no?
The signs are from
The signs don't match, right? The signs either need to match perfectly or they need to all match opposite, right? They either be all the same as the original one or all opposite. And this one doesn't do that. So what happens in D?
Also no.
Also no, for the same reason, right? So that's not the only reason that we would have to be worried about things, but signs certainly give us an easy no if they do a problem. Okay. Collinear points. That's the other one I told you was a little bit different. All right. Points are collinear when they lie on the same line. You know that. And we can determine this by finding out if the points form parallel vectors. Okay? So we actually have to create the vectors and then consider whether or not they form parallel vectors. So we start out with these points and we have to create their corresponding vectors. So once again, like earlier on, I find it easier for us to actually label the points. So let's label them A, B, and C to start. Okay, so let's do vector, AB. And it does matter the order, right? That we're doing the second vector minus the first because we are looking at terminal point versus starting point. So I have -2 minus 4, which is -6. What's my J component? It's +2. And my K component? -4. Okay. And then we can do AC. You could do BA, BC next. You actually have to determine 2 of them. So if the first 2 don't work, you might have to try the third one. So AC, so the C when I labeled C. What is my I component? 3. J? -1. And K? 2. Hope I didn't end my vector on the first one. Okay, so look at both of those. We've created vectors for the 2 pairs of points, or for the 3 points out of 2 pairs. Are they parallel?
Yeah.
They are parallel. What did you get, Noah?
-2.
Yeah. So again, depending on your perspective, so the C is either equal to -2, you could say, or -1/2. Are you good, Alex?
Yeah, I remember.
Okay, no problem. So these are parallel. I didn't write down BC, but just for the sake of having done so, let's just take a look at it. If I did BC, what would I get?
9. -3. 6.
All right, so does that also show one? It does actually, right?
C would be different though, if that mattered.
Yeah, the C would be different. That doesn't matter. The C value doesn't matter. It would still create another parallel vector.
Okay.
So on this one, no matter which 2 you picked, it would work like that. I'm not 100% sure if that would always be true or not. I need to think about that a little bit longer because I didn't think about that before I came. It might be always true, but if it doesn't work for 2 of them, I'd try the third one just to be sure.
So we need two to work.
You need 2 of them to work, yeah, for them to be parallel or collinear points, right?
Yeah, because I guess if the third one was parallel to one of them, it would have to be parallel. Like if the first
Yeah.
is parallel, if the third is parallel,
Yeah, or else
it's
they're just on the plate.
Yeah, it's like I think that it would be true for all. So, all right, our next one is maybe the most fun for the day, just because it's a little unique. We're going to use vectors to show that the points here form vertices of a parallelogram. Okay, so parallelogram. You know what that means? 2 sets of parallel sides, right? You have a picture in your mind of a parallelogram, probably even as I said it. We're looking at something like this. Now, the kicker is that they don't necessarily have to be in the order that they give them to you. So you have to be a little bit careful. So we're going to go in order and see what happens. So here's A, B, C, and D. And we're going to just find them in order. So we're going to do vector AB. So vector AB would be 1, 2, 3. That's a nice one. And then we're going to go to the next 2, BC, because it's easier to do them pairwise beside each other. So I have -3, -1, and then -2. We'll move on to CD. So CD would be 1, 2, and 3. Oh, I like that one again too, right? Our last one here, well, if we keep going in this order, would be to go back around to DA. Okay, so that means taking point A and subtracting point D. So I have 1, -3, and -4. Okay, so this is one possibility. This is the possibility of the vectors actually being in order not the vectors, but the parallelogram vertices being in order A, B, C, D, the way that we've been given them across the page, okay? Do you see any parallel vectors? You do. Which two are parallel?
A, B, and C.
Right, these two right here. So these are parallel with C equal 1, right? So you could actually even say that they're not really parallel if we were just being given them, but they're equivalent. But if you think about it, that's going to have to be the case, right? Think about a parallelogram. Not only do they have parallel sides, think 2 dimensions, but the sides are of equal length. So parallel and the same magnitude, they're going to be the same vector, so that's going to happen. What about the other two that are on there? It doesn't work, right? It doesn't work. They're not the same. The problem is that's not the only way we could have done the ordering. Now, based on the fact that we have got the AB and the CD separated, we chose to do BC, but there's another possibility. We could have done the possibility B to D and A to C. Right? Instead of it going A, B, C, D, the vectors could actually go A, B, D, C instead of A, B, C, D. We don't know for sure, so this is a possibility. Okay, so BD would be -2, and then 1 and 1. And AC is -2, 1 and 1. There they are. So these are also parallel, actually equivalent, like we said, with C equal to 1. So what really happened here? Let me show you a picture real quick of what happened. This is what we found. If I drew it well, probably didn't draw it great. We found that our parallelogram actually goes from A to B, and then B to D, D to C, and C back to A. Okay? What we originally tried, if we do this again, nope, that's not what I meant to do. Is we originally looked at the vectors doing this. It didn't work. Right? You can't just arbitrarily pick the points to go in order. They have to go the right way for this to work, obviously. So we do have a parallelogram, but it's not A, B, C, D the way I originally labeled them. It's A, B, D, C is a parallelogram. All right, that's where we're going to end today. Perfect timing to be done.